about fire galaxies, but this time about winds.
Do you want to use the pointer? Oops. Yeah, sure.
Hello, hello? Can you hear me?
Yeah, working.
Okay. And this one, how does this work? Okay, this. Oh, wait. Okay, there we go. All right, hi everyone, I'm Sasha Muratov. I'm a postdoc at UCSD, and I'm going to give you the third in this onslaught of the fire simulations. And Dushan and Daniel definitely stole some of my thunder, but hopefully I could say crazier things to keep your interest before lunch. I'm particularly interested in the galactic and the circumgalactic outflows that we see in the fire simulations, and Dushan already showed this movie, and I'm going to skip most of it because it's long and boring. You know what it looks like at the end. It's a nice disk, and here, you see these crazy winds. And this is just demonstrating that we definitely do see these circumgalactic and galactic outflows at late times. And the reason why I came to this problem, my interest from it, galactic winds are interesting to study in and of themselves. But I think my motivation for doing this work, at least, is the fact that when you add up the stellar mass, the total stellar mass and the ISM mass of galaxies, you fall short, at least an order of magnitude, towards what, in terms of what should be available to this galaxy if it were to have the cosmic mean baryon fraction. And this was a huge problem for a long time. Recently, we've had the fortune of the HST COS team investigating circumgalactic medium around sufficiently massive galaxies. And there's strong evidence that, indeed, a lot of the gas that's missing from the galaxy lies somewhere within dark matter potential, within the virial radius. And if you make some assumptions about what, just from the detections we have and do ionization corrections, you find that you can presumably account for a huge amount of this gas in the halo. And if you add it all up, you might be fine in terms of the baryon budget of the universe. The problem is when you look at these phases, it's the cool CGM, the warm CGM. This gas shouldn't really be dynamically stable. It should cool pretty fast. It should fall in. Something has to be keeping it in this phase if this is really what's going on here. So this is where galactic winds come in, because if stuff is cycling in and out of the galaxy, if stuff is being heated by processes in the galaxy, that's one. And you have other things like angular momentum, large disks. So that's very interesting. But galactic winds provide this, and it's a great time to be studying them. We know that they exist kind of ubiquitously at high redshift. If you look at sufficiently massive galaxies, they're always outflows, and they look very cool. And but what can we learn about them from the simulation perspective? Well, we start with the simplest thing that you can possibly do, which is measure the mass flux rate. And everyone does this. It's not that interesting. So why make a fuss over it? Well, the thing that I want to emphasize is that in simulations recently, it's a great time to be working on this kind of stuff because we are finally at the point where galactic winds can be considered a genuine emergent phenomena in simulation. Because in the past, you've always had to do something unphysical to create galactic winds, like just take a particle, give it a velocity, launch it out. Or turn off cooling, and then you can't really trust what you're seeing. You just have to hope it works. Finally, we have a good physically motivated model for how to do this, just like how to implement the stellar feedback processes, how to implement the ISM, simultaneously resolve the ISM all the way down to redshift 0, where the stars are forming, where you can safely resolve the Sedov-Taylor phase or account for the momentum flux of the Sedov-Taylor phase in a physical way. And this is what we start to see. So, look, this is a Milky Way progenitor galaxy, so it has about Milky Way mass at redshift 0. There's at redshift 3 when it's having one of these crazy outflows. And on the left, I highlighted the outflowing particles here in, during one of these outflows. The solid line is the virial radius. And if you look at the velocity structure, you can already see what I'm talking about here. We have, you can't really even characterize this wind with a single velocity because it's broadly distributed. And here I'm measuring it in one place, which is a quarter of the virial radius. And you can see there's some fast material that's already moved past half the virial radius. And now I'm going to play these animated GIFs in the bottom, which show what happens throughout the whole thing in terms of this process. So you see that it's a very complicated thing to characterize them in a very simple way. But the data is all there. And we can definitely do something with this to try to understand the role that winds play in moving material from the galaxy to the CGM. And I mean, this is just a few still frames for, I think Dusan already basically showed this plot, so I'm not going to spend time, but you see that the outflows can even interfere with filamentary accretion. And the other takeaway point here is that you have to be pretty careful about when you're doing an observation, and a lot of times you can't spatially resolve where the outflow is in the galaxy or how old it is necessarily. And you see that the same episode takes on vastly different appearances, characteristics at different times since birth of star formation. So again, Dusan already showed this plot, so I don't have to, hopefully I won't, but I'll explain it again, just in case anyone missed it. It's a linearly scaled plot that simultaneously shows the star formation rate multiplied by a factor of 10 just for normalization, outflow rate and inflow rate. And we see that at least at high redshift, this Milky Way progenitor galaxy undergoes this cyclical behavior in terms of star formation, inflow, outflow. In some cases, the outflow episodes will reach the virial radius. The thick dashed line is at the quarter virial radius. The thin dotted line is at the virial radius. And you could see that it's something that happens over and over again in this galaxy, and it appears to be the dominant mode of galaxy evolution for galaxies of this mass. Now, when we look at all the galaxies in our sample, not including some of the latest ones where we find true LBG progenitors, but if we look at these isolated dwarfs, this one's 10 to the 10 at redshift 0, 10 to the 11 at redshift 0, 10 to the 12 at redshift 0, and this one's 10 to the 12 at redshift 2. The behavior, I mean, there's some differences here, definitely, but you can still essentially characterize that every halo is undergoing a pattern like this at high redshift. So what can we learn from this? Again, that was just the simplest thing you could do, flux through a spherical shell over time. Now, in terms of broadly averaging it all out, we can also do that in the simplest possible way. Just that one interval I showed you between redshift 4.5 and redshift 2, that's one grouping. Another grouping is between redshift 2 and 0.5, and another grouping is redshift less than 0.5. And we consider the mass loading factor, which is defined as the ratio of the outflowing flux at a quarter of the virial radius to the star formation rate, versus the circular velocity. And it has this pattern, and as I addressed before in a question, it's kind of interesting that we seem to observe this kink around 60 kilometers per second, where it clearly goes from having a very steep slope to a very shallow slope. And this is somewhat expected in theoretically motivated wind models, where if you're in the energy-driven regime where the supernova heat all of the material, then you are in this place where the slope is expected to be something like -2. We find something like -3, so it's even steeper. Whereas if you're in the high mass regime where supernovas cool and effectively deposit some momentum flux to the gas to drive a wind, then you're in a regime where you expect the AIDA to go as circular velocity to the first power. And we find this interesting redshift evolution with this. It's kind of tricky because we have 3 bins and we don't even use the last one for the fit because it's, here it seems to go through the points pretty well, but here, as Dusan pointed out, there's something up with these high mass, low redshift galaxies. And we also observe a correlation for AIDA versus stellar mass. which does not involve with redshift and is pretty robust over all the orders of magnitudes. So AIDA is a great quantity, the mass loading factor. Observers have a hard time measuring AIDA. It's not very useful to them for the most part, I think. That's more for the semi-analytic people. In terms of what observers can measure, it's the wind velocity. And we find that we seem to have this correlation for circular velocity versus wind velocity, which sort of makes sense. I mean, if you're not going to be able to launch a wind if you're going slower than the circular velocity. It's not going to go anywhere. It's going to get, by the time it reaches a quarter of the virial radius, it's going to turn back around. If we look at our 95th percentile wind velocity, which is this line, the dashed line here is median, the shaded region is 25th to 75th percentile. Each fit is independent of each other, by the way, so there is no prescribed reason why these slopes should be the same, but they are. And it's, it's something that's been seen in observations before. The 95th percentile is similar to some work that's been published. This is more disingenuous, but stellar mass also correlates with wind velocity, and so does B-band magnitude. That's all I'll say. At low redshift, this is the important thing, right? So something really changes in our feedback model. And I mean, it's not the model itself, it's something about the galaxies changes. The model is the same. And in the case of a dwarf galaxy, an isolated dwarf galaxy, 10 to the 11 solar mass at redshift 0, about 10 to the 9 solar masses is like a dwarf starburst. It's still undergoing this burst-bust cycle. But if we look at one of our best candidates for being Milky Way-like galaxy, because it does have this extended thin disk, it has a high star formation rate at low redshift, and it's continuous. But if we look for outflows at a quarter of the virial radius, we don't find them. So something's going on. Our first clue comes from the fact that star formation, contrast what's going on here to what was going on at high redshift. We have organized motion in a nice disk here in the gas, and stars here, the black is the total stellar distribution, and the red is the young stars that are forming in this galaxy. They're forming all over the place in this giant 60 kiloparsec slice of spatial region. Whereas before it was mostly concentrated in the center, and you really had this super bubble. Here, it's unlikely that you're going to have an opportunity for a super bubble to form when the young stellar density is so relatively low. So this gives us a hint to consider, instead of just star formation rate, let's see if star formation surface density might not be driving the outflows. And in that particular galaxy, it's spot on exactly what's happening. So if we look at, black is still star formation. This is a log-log plot, so it's a little crazier here. Red is the outflow rate at a quarter virial radius. Blue, in this case, is the star formation surface density. So you see between redshift 2 and 1, the blue is going crazy like the star formation outflow. Below redshift 1, though, it drops off below about 10 to the minus 1 solar masses per year per kiloparsec squared, which is an amazing coincidence, because that's since 2000, Tim Heckman and others have argued that this appears to represent some kind of threshold for a starburst to be active. And so we were really excited when we found this. We thought we figured it all out. When we looked at one of our other Milky Way progenitors, that's not really a Milky Way progenitor at all, but about the same mass, but it has much lower star formation rate at low redshift. It's under 1 solar mass per year star formation, and it just kind of tapers off, and it's very spheroidal. In this case, we can't really, there's still a change in the behavior of star formation surface density, but it more or less just mirrors what's happening in the star formation rate, and it definitely does go above, the threshold sometimes. So there's something, it's not, you can't just publish a paper saying it's all star formation surface density based on one halo. And so far we only have 3 of these Milky Way progenitors, so we need to go back to the drawing board, figure out what's going on. Before I said I was averaging all the data over these broad redshift intervals, but there's really no reason why we have to do it that way. The fact that this kind of evolution lends itself perfectly to this sort of discretization of each separate burst as being independent from each other. and basically studying each separate burst, studying the conditions of the galaxy at the time of the burst, and trying to understand what the conditions of the galaxy are using the same feedback model to see how this behavior can change at low redshift. And another question that's related is just generally can we more finely understand what determines the mass loading factor and other wind properties. And just blindly we consider the star formation surface density, escape velocity, which traces gravitational potential depth. It's the escape velocity from the starburst. And star formation rate, which in this case is meant to be a proxy for inflow rate, just like how much gas the galaxy is getting. And individually, these don't look great. Star formation surface density, which is up here, looks the best, but the scatter is huge. And you kind of have halos clustered together on this plot. So the fun thing to do is combine all three, and you get this sort of correlation. So it has a better chi-square than surface density alone. And more importantly, it looks kind of the same, so I'm not going to, this is preliminary work. But the nice thing is that it does bring these simulations more close together so that you can kind of see the same general behavior happening across different simulations. So I'm going to quickly mention Shengqing Ma's paper. Shengqing Ma is speaking next, but he's speaking about escape fraction. He also studied the stellar mass gas mass, or stellar mass gas metallicity and stellar mass metallicity.
Can you do this very quickly?
Sure. And we also did the metal flux and everything, and we're working on a follow-up. And I'll just throw up.
Okay, good.
Okay.
Okay, thank you. Can Shengqing Ma get set up for the next talk? Thank you. Meanwhile, questions for Sasha. Let me start over here.
The thing that observers usually see here, the cold outflows, the cold phase of the outflows.
Yeah.
So do you split the outflow in the different properties, in the different phases? And what's the velocity of the cold phase?
Yes, we've started to look at that. And our outflows are definitely multi-phase when I measure them at a quarter of the virial radius. In general, the cold phase tends to, less than 10 to the 5 Kelvin tends to dominate. The high temperature component has a higher velocity. That's about all I'm ready to say about that, but it's something that we started to look at. Yes.
Other questions?
So you see that the winds sort of shut down or ramp down towards redshift 0 as the halo grows. Does that kind of give you any insight about what might be going on in bigger halos where stellar feedback alone can't launch winds, that maybe they're reaching these high masses where the outflow rates shut down earlier at high redshift perhaps?
Yeah. So my current understanding from preliminary analysis is that I mentioned that I was looking at escape velocity as a tracer, and there tends to be this before, the one that I showed, it had a nice flat disk and everything, but even before that, something happened in that halo where it transitioned from being mostly dark matter dominated in the core to being baryon dominated in the core, which significantly increased the central density. And that seems to stabilize the galaxies at against these huge outflows that disrupt a large portion of the ISM. And when you reach that stage, when they're baryon dominated, that's my current hypothesis for what's happening. I have not yet proven it.
So
and
depth of a potential well kind of effect.
yeah, but the depth of the potential well may be the first thing that sort of happens, and then it drives some of these other things. And combined with the fact that redshift evolution generally is going to starve you of gas at late times, because you just cause the IgM gets thinner and you don't have as much accretion, and you have maybe a hot halo that's preventing some accretion.
So why don't we move on to Shengqing